So today we're going to talk about the average value of a function. It's also called the mean value of a function. And it's basically like this, okay? If you're trying to find the average of like your test scores, you add them all up and divide by how many there are, right? So to find the average value of a function, that means all of these function values, all of these y values from this right here, which I'll label it A, right here, this left endpoint, all the way to this right endpoint B, we want to add all these function values up and divide by how many there are and get an average. But how can you do that, right? So how can you do that? Because how many are there in here? Well, there's infinitely many. How do you add an infinite number together? You really can't, right? But there is a way, right? You can't do it the normal way that you thought of back when you learned about average in elementary school or maybe junior high, okay? So to build on this, okay, we're going to start with something kind of simple and we're going to build to it. And we're going to first just do, okay, what if we just had three of them? Like, what if we just had three values? Okay. So let's say we have this value. Okay. So I'm going to use this value right here, this function value I'm going to label this one C sub 1. So this is the x value, C sub 1. And so this right here, this height right here would be f of C sub 1. And then let's do this one. And this would be C sub 2. And then this one would be C sub 3. That's supposed to be straight up and down. Okay. A little crooked, huh? Okay. So how do you find average? Okay. So how do I find the average of these three values, right? These three function values right here. So what I would do is, since there's three, I'm going to take f of C sub 1, and I'm going to add f of C sub 2, and I'm going to add f of C sub 3. And I'm going to divide by how many there are. And in this case, there is 3. Okay, so I'm going to write this another way. I'm going to start to write this in sigma notation. Okay, so dividing by 3 is the same as multiplying by 1/3. So this would be 1/3 sigma. Okay, and it'd be f of C, and these are what's increasing, though, C sub 1, 2, and 3. So I'm going to call this C sub K, and I'm going to start K at 1 and end it at 3, because then that would give me C sub 1 in here, and then 2 would give me C sub 2, and then 3 would give me C sub 3, f of C sub 3. Okay. All right. Now, what do we know about this? Since there's 3, okay, we know that the width of each of these, our delta x, would be b minus a and divide by 3. So what I'm going to do right here is I'm going to multiply, and there's going to be, I'm going to replace this 1/3, and I'm going to show you what I'm going to replace it with by doing this. Okay. And this is the ingenuity of somebody who first figured this out. Okay. Is that they realize that if I multiply this side by 1 over b minus a, and also this side by 1 over b minus a. All right. And so what happens here is I get the b minus a here and the b minus a here cancel. So on this side, I'm going to be left with 1/3, which is this 1/3 right here. And this left-hand side, I'm going to be left with delta x over b minus a, and that would equal 1/3. So that's true for this problem. So that means this 1/3 can be replaced with delta x over b minus a. And that's what I'm going to do. So I'm going to write this as delta x over b minus a. And then sigma k equals 1 to 3 f of c sub k. All right. Now, there's the delta x is going to be a specific number because there's 3 of these, right? So because this is a number, I can actually bring this in, because if I wrote this out, I'd be adding them, right? And then I would have to distribute the delta x. Well, I could also bring this delta x in and have the delta x inside the sigma. So really, this could come out to become 1 over b minus a sigma k equals 1 to 3 f of c sub k times delta x. Now, this right here, this was the sum of these function values. This is different. This is the sum of each of these rectangles. And so right here, this is the height of the rectangles, right? When I start putting the 1 in 2, this is the height of the rectangle, and this is the width of the rectangle. So if I found the average value of these, okay, I could do it like this, add these 3 values and divide by 3. But this is saying something different. This is saying if I get the area of these rectangles and add them up, and I multiply that by 1 over the upper limit of integration minus the lower limit of integration, okay, or right endpoint and left endpoint. This is going to become an integration problem if you didn't know. All right, then I can just multiply the area of those 3 rectangles added together with the 1 over b minus a, and I would have the average. So it's a new way of doing it, right? It's not doing it this traditional way, but doing it this way. Okay. All right. But that doesn't work because we want to add all of them, right? So what I'm going to do next is I'm going to double the number of rectangles, and we're going to have 6. Okay. And so we're going to build from this idea of 3 of them, and we're going to continue building until we figure this problem out. All right. So once again, this is the left endpoint is A and the right endpoint is B. And right in between here, going straight down, this would be C sub 1. This would be C sub 2. C sub 3. This last one over here, I'm going to not do all of them, would be C sub 6. Because there's 1, 2, 3, 4, 5, and 6. Okay, so to find the average of these 6 function values, we would take f of c sub 1 plus f of c sub 2 plus f of c sub 3 plus, and I don't want to write them all, so I'm just going to write a dot, 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 plus, and then the end would be f of c sub 6. And we would want to divide that because there's 6 of them. We'd want to divide by 6. So once again, we can write this in sigma notation, right? This would be 1/6 because dividing by 6 is the same as multiplying by 1/6. The sum of all of these function values, right? And that would be k equals 1 to 6 f of c sub k. But just like earlier, delta x we know is b minus a over 6, right? Each of these widths is b minus a and divide by 6. So once again, I'm going to multiply both sides by this by 1 over b minus a. And so I would get delta x over b minus a would equal 1/6. So what does that mean? That means this 1/6 can be replaced with delta x over b minus a. So this becomes delta x over b minus a, just like before, sigma k equals 1 to 6 f of c sub k. So, okay, because these delta x's are all the same, okay, and I could bring this in and multiply it. So then that means 1 over b minus a sigma k equals 1 to 6 f of c sub k times my delta x. And once again, adding these 6 functions values together and dividing by 6 is one way to get the average. Okay, you can do that. You can do it this way when there's a finite number like 6. Okay, but this is saying there's another way we can do it, right? We can do the same exact thing by taking the area of each of these 6 rectangles and adding them together and multiplying by 1 over b minus a, which is where I want to start integrating and to where I want to end the integration, right? Okay, so let's take this one more step. Instead of 3, instead of 6, what if we have n of these rectangles? Okay, and let's take a look at that. So this time we're going to make n of these. Okay, so again, this left endpoint is A, the right endpoint is B, And each one of these would be C sub 1, C sub 2, and so on, right? This last one would be C sub n, okay? So if I wanted to find the average of n of them, I would take f of C sub 1 plus f of C sub 2 plus f of C sub 3 plus, I can't write them all, okay? Dot, 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 plus, and the last one would be f of C sub n. And how many would I divide by? Well, how many are there? Well, there's n of them, right? So that'd be dividing by n, and that would give me the average of a finite number, right? Of n of them. That's what we've been doing the whole time. It's just we had a finite, like we stopped at 3 or stopped at 6. Okay. So how can we rewrite that? Well, what we can do is we can rewrite this as 1 over n, and we can write this as sigma notation. So the sigma, we'd have sigma, and we started at k equals 1 to n, and it'd be f of C sub k. All right. So earlier we were able to change this 1 over n to delta x over b minus a. Can we still do that? Well, let's take a look. What is delta x? Well, delta x is going to be the right endpoint minus the left endpoint. So b minus a over, and how many are there? Well, there's going to be n of them, right? So if I multiply by both sides of this equation by 1 over b minus a, 1 over b minus a, that's going to give me a left side of delta x over b minus a equals, and then this side would be just 1 over n. So same thing happens, right? This 1 over n can be replaced with delta x over b minus a. So that's equal to delta x over b minus a sigma f of C sub k, and I should have put my lower and upper limits in. So this is k equals 1 to n. All right, and then once again, the delta x can come in here. So this becomes 1 over b minus a sigma k equals 1 to n f of C sub k times delta x. All right, so once again, the same thing works, right? Even if there's n of them, right? So how do I get it so I add all of them up? Like, how can I go about adding all of them? What, how many are there? What would we need this n to be to add all of them? Well, what happens is, as we made n get bigger and bigger and bigger, right? What was happening to these widths? They were getting smaller and smaller and smaller. What if n goes to infinity? Then what that means is we're putting so many rectangles in here that the left side and the right side, okay, I'm trying to point to it with my fingers, the left side and the right side actually come together, and it's like it no longer becomes a rectangle, it's like a line segment. And basically what you have is an infinite number of line segments adjacent to each other. So basically you're getting all of the function values, okay? So, all right, that's how we can find the average of them, all right? We have to do a limit, okay? So the average of f of x would equal 1 over b minus a times, and this would be the limit as n approaches infinity of sigma k equals 1 to n f of C sub k times delta x. Does any of this look familiar? And it should, right? And here's where the integral comes in. We should be recognizing this. This is the area of a rectangle. These are all my heights. These are all my widths. Since n is going to infinity, this delta x is becoming my dx. This is an integral. So the average of f of x, and I should have said this on this interval a to b, this winds up being 1 over b minus a times the integral from a to b of my function f of x dx. So that's how we're going to find the average value of a function. It actually takes calculus to do it. Okay. And it's an integral. All right. So let me slide this up and we'll formally. So the average value of function, if f is integrable, that's a hard word to say. All right. If it's integrable, that means we can take the integral. All right. On a to b, its average or mean value on a to b is 1 over b minus a times the integral from a to b of f of x dx. Now, I prefer this one. It's probably because I was taught it this way, but there's another way to write this. And I want you to know that some math professors and some math teachers write it differently. It's not wrong. If you're multiplying 1 over, this is a fraction, 1 over something times something, right? This can actually be 1 times this over b minus a. And that's just another way some people write it. They write it as the integral from a to b of f of x dx. And we take that integral and we divide that by b minus a. So it's just an alternative way of doing it. If you like to do it this way, that makes sense to you, go for it. You can write it this way. There's no problem on me, my part, no problem with you writing it this way. Okay. You're going to see me do it this way. And it's just, that's the way I learned it. Okay. All right. So let's do some problems. Okay. Right now, here's a problem that we're faced with right now. And the problem is we need this average value and the mean value theorem to do the next thing. We need that to figure out how to do these, okay? To do these definite integrals. So we've been doing them, and you're like, Mr. Mitchell, we've already been doing them. Yeah, we've been doing them, but we haven't been doing them algebraically. We've been doing them from a graph, right? I've given you the areas, or there's simple geometric shapes that you can find the area. Or the other option to do this right now is we use a calculator, okay? Monday, my plan, well, this is what I have planned for Monday, is I'm going to show you using the mean value theorem and some other theorems, like how to do this, okay? The connection between this and how do we do this calculation, okay? It's kind of like, how do we do derivatives? All right. Okay. All right. So let's do some problems now. So for this problem, okay, regions A, B, C, and D in the figure above are bounded by the graph of the function f and the x-axis. Okay, so we have these regions A and B. B is below the x-axis, C is above, D is below. All right, the area of region A is 15. So that would mean the integral from -8 to -4 would be positive 15. And then the integral from -4 to -1, since this area is 14, the integral would be -14. Remember that, okay? And then C be 9, and then D would be the integral would be -12. The area is 12, the integral is -12. Okay. So here's a question: what is the average value of f on the interval -4 to 8 in simplest form? Okay, so in simplest form. There we go. I was thinking it was out of focus. All right. All right. So we want to start right here at -4, and we want to end it right here at 8. Okay. So to find the average value, we would take 1 over, and it would be 8 minus -4, because this is our B and this is our A. So it'd be 8 minus -4 times the integral from -4 to 8 of f of x dx. Okay, so 1 over 8 minus 4, that'd be actually 8 plus 4, right? So that'd be 1 over 12. Times the integral from -4 to 8 of f of x dx. Okay, so now so this is the integral from -4 to 8. Well, we can do that because we know the areas, right? So this is going to become 1/12, and I'm going to use a bracket here. And then, okay, so I know I'm going to start integrating at -4, and I'm going to break it up into this integral, right? So I know that since B is 14, and actually I probably should have written these in. Okay, so I know A is 15, B is 14, C is 9. That would make it easier. And D is 12. Okay, so because this region is below the x-axis, I know when I go to integrate, this is going to be a negative value. So it's going to be -14 or -14. And then we're going to go to the next region, which would be the integral from -1 to 2, and that would be +9. And then we want to go from 2 to 8, and because it's below, that's going to be -12, so I'm going to write -12. Okay, so now it's just a matter of figuring this out. So this would be 1/12, and then times, and -14 and +9 makes -5, and -12 makes -17 rather. Okay, so that makes this -17/12. And if you can, I want you to simplify this, okay, in simplest form. But 17 is a prime number, so you can't simplify this anymore. Okay, so that's our final answer, is -17/12. Okay, so what the heck does this mean? This means, all right, if I were able to do it the traditional way of finding an average, if I took all of the function values starting at -4 and all the way to 8, if I added all of these, and I'm not even putting them all right because I'm drawing a finite number here. If I took all of these function values and added them up and divided by how many there were, if I were able to do that, it would have to come out to be -17/12. The problem is you can't do it because there's too many, right? There's infinitely many. But yet we can still find the average of them, even though we could never write them all down. We couldn't because there's infinitely many, but we can still find the sum. That just boggles my mind that we are able to do that. Okay, but that's what this means. It means that if you add all of these up, this is what it would come out to be. Okay. All right. So the first 4 problems, okay, on Delta Math are Delta Math problems. Okay. And so for the assignment today, all right, if you get one wrong, you have to do a 1 to make it up, right? Okay, so that's the first 4 problems. The rest of the problems are actually problems from our textbook. Okay, and what I've done for problems 5 through 12 on the assignment 7-6 on Delta Math is I'm giving you it can't generate another problem to make up for the one you missed. Okay, but what I'm doing instead is it will mark it wrong. Okay, and what you need to do is it'll give you 3 attempts. So you'll have 3 attempts at every problem to get it right. Okay, so if you get it wrong, you have a second and third try at it to get the problem right. Okay, all right, and the problems are going to be similar to the next ones I do. Okay. So we have this function f, okay? It's the square root of x plus 1 when x is between 0 and 3, including 0 and 3. And it's 5 minus x for when x is bigger than 3, but not equal to 3, but when it's less than or equal to 5, okay? And so we want to use function integrate. So I haven't shown you, we don't know how to integrate yet, right? But we are going to do the problem still because we can calculate, we're going to do the integral with our calculator, all right? Okay, so first of all, this is a continuous function. This is a continuous function. What weird things can happen when it switches pieces, right? When it's at 3. So what if we put 3 in here? 3 plus 1 is 4. Square root of 4 is 2. So when x is 3, this function gives you 2. What does this one give you? Well, when you put 3 in here, it will also give you 2. So there's no jump discontinuity or anything weird happening when we switch pieces, right? Okay, they're connected. This piece is connected with this piece, so it's continuous. All right. So how do we find the average value of f of x on the closed interval from 0 to 5? Okay, so that means we want that would be saying in essence 0 to 5 like this. Okay, and we want to find the average value of f. Okay, so that would be 1 over 5 minus 0 times the integral from 0 to 5 of our function f of x dx. Okay, so that becomes 1/5 the integral from 0 to 5 of f of x dx. Now there's a problem with this because there's 2 different pieces. So what we have to do is we have to break this integral into the integral from 0 to 3, and then we have to integrate from 3 to 5. So this becomes, not add, we should have an equals here. Let me put it white out. That's why God made white out, right? For me. Okay. So this is equal to 1/5. And I'm going to use a bracket here. Okay. And then the integral from 0 to 5, we're going to have to write the integral from 0 to 3. So that'd be the integral from 0 to 3 of the square root of x plus 1 dx. And then we also need to add to that the integral from 3 to 5 of 5 minus x dx. And then I need to close my bracket. Okay. So you guys do not know how to do this yet. Okay. This is, next week's, this is days to come. We're going to figure this out. Okay. How to do these by hand. But right now we don't know how to do it. And we don't have a geometric shape. Okay. So you just can't do this. All right. So we're going to put in our calculator. So I'm going to go to my calculator and I'm going to show you how to enter this. And then we'll come back and we'll write down the answer. So we're going to go and create a fraction. So 1/5. So alpha x and then 1/5. And then we want to put in a left parenthesis and then we want to integrate, right? So to get the integral, we press alpha and then window and then select number 4 because that's the integral symbol. And then from 0 to 3. And then this would be the square root of x plus 1. So square root and then x plus 1 and then dx. So that's the integral from 0 to 3. And then we also need to add in the integral. So alpha window 4 from 3 to 5. And then we want to type in here 5 minus x and then dx. And then close our parenthesis for the sum of these two integrals. And then we press enter. We want to make sure, I should have said this at the very get-go, right up here, we need to make sure we're in radian mode. It won't matter for this one because it's not involving trig functions. But if it was involving trig functions, we'd want to make sure we're in radians. So if I press enter, we get 1.33333. So rounding to 3 decimal places, because that's what you need to do for the AP exam, this is 1.333. Now, one thing we should recognize is, and I say this, I'm going to say this again, is that if you see 0.3 repeating, we should recognize that as the fraction 1/3. Okay, so let's go back and record this on our paper. So from our calculator, we got an approximation of 1.333, right? We went around to 3 decimal places, 1.333. Now, our calculator said 1.3333 ongoing, right? We should recognize that 0.3 repeating is actually 1/3. So this decimal right here is 1 plus 0.333. Okay, so that means we have 1 plus 1/3. Well, 1 plus 1/3, this is 3/3. So really, this actually comes out. We could actually write the exact value. This comes out to be 4/3. Okay, so a repeating decimal, I would want you to rewrite it as a fraction. Repeating decimals can be written as fractions. Okay, and I would like you to be aware of that. Okay, so that's that problem. Okay, let's go to the next problem. So traffic flow in this problem is defined as the rate at which cars pass through an intersection measured in, okay, and this is the units, cars per minute. That's the units attached to this function, okay? The traffic flow at a particular intersection is modeled by the function capital F, defined by 82 plus 4 sine of t over 2 for 0 less than or equal to t less than or equal to 30, okay? So what is the average traffic flow, right? So this f of t, this is traffic. This function gives us the traffic flow. Okay, so it gives us the traffic flow, and I want to know the average of the traffic flow between 10 and 15. So how can I calculate that? All right, so we can do an integral, okay, because we want to find it between these two time values, okay, and so we're going to integrate, or not integrate yet, we're going to take 1 over 15 minus 10 times the integral from 10 to 15, and it would be f of t dt, capital F of t dt. All right, so 15 minus 10, that's 5. So this becomes 1/5 times the integral from 10 to 15 of, and I'm going to put this in parentheses, it's 82 plus 4 sine of t over 2, close the parenthesis, and then dt. Okay, so we don't know, again, we don't know how to do this. Okay, we don't know, whatever, because it's not a geometric shape. I didn't give you the graph. I didn't give you any areas. Okay, so how do you calculate this? Okay, so we're going to have to use the function integrate. And I should have said that. I should have said this in here. This is function integrate, like we did this one up here. Okay, so this is going to be equal to, or approximately, okay? And you know what? I'm sorry. I wanted to leave some space because I actually want to talk. So let's skip a little bit of space down. And I should be putting approximation, okay? So we're going to go to our calculator and we're going to put this in. So again, we want to find the average value. So we're going to press alpha x to get the fraction. And this is 1/5. And then the integral. So alpha window number 4. And we want to integrate from 10 to 15. So we'll go 10 to 15. And then again, our function is 82 plus 4. And then sine of, and then t over 2. So another fraction. And I'm going to use x instead of t because you can do that on the calculator. So x over 2. And then we want to get out of the fraction, and then we want to close the parenthesis because that's going to close it for the sine function. And then this parenthesis right here that I'm pointing to ends the entire function. Whoa, I almost said a bad word there, huh? Okay, dx. Woo, Mr. Mitchell's a little embarrassed right now. Function, right? If you can't laugh at yourself, what can you do? So sorry about that. All right, press enter, and you get 81.899. Those are little Easter eggs that I hide in my videos, huh? You have to watch the whole video to hear me say stuff like that. Holy cow! Okay, so let's go back and record this on our paper. So from our calculator, we got 81.899. Okay, so now this is the big deal, okay? I want to indicate units of measurement. What are the units? Well, I'm finding the average of this function, right? So the units should be the same units because I'm just like adding them and dividing by how many there are, right? So the units should be the same. This is cars per minute. This unit right here should be cars per minute. Okay, let's verify that it would be cars per minute, okay? All right, so this integral right here, okay, remember these are our function heights, right? These are the values of the function, all right? And this is our width right here, okay? So if we were to graph this function, okay, what we would have over here on this left-hand side, the units would be cars per minute. And the horizontal would be this, right? And it would be minutes, because that's the time unit. That would be our delta t, okay? Our delta x is delta t in this time, because t is taking the place of x, and t for time, all right? Okay, so what does that mean? That means if I made these rectangles that I've been talking so much about, right? The width would be minutes, and the height would be cars per minute, which means the units on this would be cars per minute times, and my dt units would be minutes. And if I were to multiply that, what would I get? Well, you should be thinking, what, you're going to get cars. Yeah, you're going to get cars. When you integrate this, you're going to get, okay, so I'm going to tell you what you're going to get. We haven't learned a lesson on this yet, but we're going to, okay? What you're going to get is the number of cars that have traveled through this intersection. So if we have this rate, we're multiplying by time here, minutes, right? We're going to get this unit right here, cars. This is cars. Well, what did I just say just a minute ago? This needs to be cars per minute, right? Because we're finding the average of it. Well, how the heck does this become cars per minute? Well, this is how. Over here, this one this has no units attached to it, but the 5 came from this 15 minus 10. Those were t values, right? Those came from these t values. Those t values, this is 10 minutes and this is 15 minutes. So this 5 right here is actually 5 minutes. So we're taking this, that's cars, and multiplying it by the units 1 over minutes. And what would that give us? That would give us cars per minute. So I realize you don't have to go through all that analysis to get the units, because you go, wait, I'm finding the average of this. The units should be the same. Okay, that's at least how we should be thinking, okay? But I wanted to show you that, yeah, we do actually get the same units, okay? Because here the minutes cancel, and we're left with cars, and then we're going to multiply cars by 1 over minutes, and that would give you cars over minutes, right? Or cars per minute, like what we have right here. So I just wanted to kind of go into a detailed understanding of like, what are the units on this? Okay. By the way, this was an old AP exam question from many years ago. Okay. And you were able to use your calculator on it. All right. This is one of those problems. All right. Have just a little bit more to go over with you guys. We need to talk about what's called the mean value theorem, which is pretty straightforward. It's similar to the average. We kind of use the average value function. Be careful. There is average value of a function and average rate of change. So be careful. There's a difference. Average value of a function is what we're doing right here. Average value of a function. Average rate of change is the slope, okay? It's the slope between 2 points, okay? All right, so we got to be careful on that. Average rate of change, average value, 2 different things. So for this, we should know, okay, so this, let me write this. This is f of x, and all of these are going to be f of x, okay? So I'm only going to write it once. So at this point, we should realize, okay, this shading represents the area under the curve between the curve and the x-axis. And so this area and the integral are the same thing, right? Okay, so this has area, and we could get this area by taking the integral from a to b of f of x dx, okay? Now, let's take a look at this, okay? So this is a rectangle, all right? And this rectangle has area. It's the shaded region in here. What is that shaded region, okay? Well, I know the function height is f of a. And a is the left endpoint. A is this value right here where we're finding the integral at, okay? So what this is, and then, wait, hold on. This would be, this length right here would be b minus a, which means the area would be equal to f of a times b minus a. Okay, so this shaded region, that's the area right here, okay? Now, this area right here is definitely larger than this one, right? So this area right here and this rectangle, the area here is going to be larger. This rectangle, and all of these areas are between A and B, okay? This area right here is also between A and B, but B is right here on the endpoint. And I made these so that this one's the minimum and this one's the maximum, just it makes it easier to see it, okay? So now the area of this rectangle, okay, would be f of b. And this dimension would be b minus a. So the area of this one would be equal to f of b times b minus a. So what I know is if this rectangle here is smaller than this one, right? Because this is only this part of it, right? If I raise this rectangle up, okay, and usually I have an animation to show you guys, but it's really hard doing this distance learning, okay? If I bring this up, if I bring this rectangle up, okay, if I come all the way up to this point right here, that's this, and it's too much, right? So what has to happen is I can bring this up, okay? I can bring this height up until I reach the same area as this one. And that's what this represents, okay? Is I'm still going between A and B, but what I'm doing is I'm going to stop it once this area reaches the same area as this one. Okay. So this is too small. This is too big, right? We've gone too far up because definitely this area is bigger than this one, right? And we haven't gone up far enough. So somewhere in between this value right here, f of A, and f of B, right? Somewhere in there, there has to be a height that gives you the identical area as the integral of the area of the integral here. Okay. So what is that? Well, it's right about here. Okay. And I'm going to call that C. So this area and this area are the same. And you can kind of, well, you can't do this without calculus, all right? But you can kind of see, it kind of makes sense because this extra part right here kind of almost fits in this, right? Okay. All right. So what does this mean? Well, that means this dimension, okay, this length of this rectangle would still be B minus A. The height of the rectangle is now f of C. And where is C? Well, C is somewhere in between A and B. So what this is telling me is that f of C times B minus A. So this height of this rectangle times the difference between A and B, which is this side of the rectangle, is equivalent to this integral. The integral from A to B of f of x dx. Okay, so what I want you to understand is too small, too big. There has to be a rectangle, somewhere in between. Like if I came straight up like this, there has to be some rectangle. This is too much. This is not enough. There has to be some rectangle in between here where it would be the same as this integral. Okay, so let me go and let me show you this. So from what we saw is that if we have the integral from A to B of f of x dx, that's some area, right? And so that can be calculated, okay, by taking f of some c, where c is in between A and B, right? C is at some point C and A and B. That height, whatever that height might be, times B minus A would be the same as this integral. Okay, so this is the area under the curve. This left side is the area under the curve. This is the area of some rectangle with height f of c. Okay, so let me show you what this actually means and what we're going to use this in this next problem. Okay, so this is an equals right here, so that means this is an equation. So this b minus a is a number. So what I'm going to do is I'm going to multiply both sides of this equation by 1 over b minus a. So this left hand side becomes 1 over b minus a times the integral from a to b of f of x dx. Now we should recognize that. And what this equals is f of c. So what the heck does this mean? Okay, what is this right here? Well, this is the average of f of x on the interval a to b, right? This is the average value of f of x between a and b. So average of f of x on this interval a to b. What this means is that c is somewhere in between a and b. That means that the average value of the function takes on some function value, right? So there has to be a function value, okay, that is exactly the same as the average value of the function, okay? So this is the function value at c. So what this allows us to do is it allows us to figure out, okay, where does this happen, right? What is the X value that where we can put that into the function, and that is the identical number as the average value of the function. Okay. It's kind of like this. All right. If you had a test score, okay, let's say your test scores on tests were between 80 and 90, okay? And let's say you averaged your test scores and you got a test score of, let's say, 86, okay? But you took so many tests that you actually scored every single value between 80 and 90, okay? So your average was 86, right? That must mean that you had to have hit 86. You had to have at least had one test that was 86. If you hit every test of every for every score between 80 and 90, all right, there had to have been a test that one test, at least one test that you got an 86 on. Okay, that's kind of what it is. I don't know if that's the best explanation. I just thought of that right now to say it. All right. But here we go. Okay, so use function integrate. So we're going to have to use that again, okay, to find the average value of the function on the interval. So we want to do that first. And then at what points in the interval, okay, so it has to be in the interval. That's the key. It has to be in the value we find has for this to happen. It has to be in between A and B, okay? Does the function assume its average value? I mean, in other words, the function is the same as the average value of the function, okay? So let's do the first part. Let's find this average value, okay? So here's our function, f of x is 4 minus x squared, and we want to find the average value on this interval 0 to 3. So that'd be 1 over 3 minus 0 times the integral from 0 to 3 of f of x, right? Which in this case is 4 minus x squared dx. Okay, so that comes out to be 1 over 3 times the integral from 0 to 3 of 4 minus x squared dx. Okay, so we're going to put this into our calculator and we'll come back and write it down. So now we want to put in 1/3. So alpha x, so 1/3. And then the integral, so alpha window, and then number 4. And we want to go from 0 to 3. And our function is 4 minus x squared. And then dx. And we press enter, and we get 1. All right, so let's go back and record this on our calculator. So from our calculator, we got a value of 1. Okay, so I'm going to use this. Okay, this 1 is the average value, right? So I know that if I take 1 over 3 times the integral from 0 to 3 of, in this case, 4 minus x squared dx, that has to be the same as putting some number into the function and getting the output out. So the number I'm going to put in, I don't know it yet. I'm going to call it C. Okay, so automatically I know that this from up here, this is 1. So I have 1 is equal to f of c. That would mean 1 is equal to, if I put c into my f function, that'd be 4 minus c squared. Because f of x is 4 minus x squared, okay? I'm going to move the c squared over to the left-hand side and the 1 over to the right-hand side. That would give me c squared is equal to 3. I'm going to square root both sides. That would give me the absolute value of c is equal to the square root of 3. That would mean c is equal to the square root of 3 or negative square root of 3. All right. Now, there's a problem. One of these doesn't work because our c value must come in the interval that was given, right? And the interval that was given was 0 to 3. So this one right here, this negative square root of 3, is not a value that works, okay? Because this is not in 0 to 3. Okay, so our only value is c is equal to the square root of 3. So at what point is in the interval does the function assume its average value? At the point x equals the square root of 3. Okay, that's where it's going to happen. Okay, so I want to show you that if we took this integral, right, these are kind of saying the same thing. Okay, this one is just a modification of this one. All right, and this one's used more. So I want to show you that this would be true. Okay, so the area under the curve, well, the area under this curve from 0 to 3 would be this, right? 0 to 3 f of x dx, okay, which would be 4 minus x squared. Okay, that's equal to f of the square root of 3, right? Because that's what we found right here, okay, times b minus a, which would be 3 minus 0. So this is the height of my rectangle, right, from the previous page. So this is my height of my rectangle. This is the horizontal dimension, okay? So, okay, we're going to go and we're going to put this into our calculator. Okay, so let me go and do that. So from our calculator, we got this left-hand side was 3 and equals. And if we put square root of 3 into our function, that would be 4 minus the square root of 3 squared times 3. So that's the area under the curve is 3, right? And so the area of this rectangle would be, well, this would be 4 minus 3. Times 3, right? And 4 minus 1, or 4 minus 3. Whoa, 4 minus 3 is 1 times 3. See, we get 3 equals 3. So the area of this rectangle and the area under the curve are the same, okay? Do you have to show this? No. This is just verifying that we found the right value, okay? We found the right value because at this x value, it causes the height to be the right value that gives us the area under the curve and the area of the rectangle to be the same. All right. Okay, guys. So Monday's going to be a big deal. Okay. Monday's going to be showing you actually how to do these integrals by hand, and you won't have to use a calculator anymore. Okay. All right, guys. That's it.